Is this the world's best Mandelbrot renderer? Let's find out. This project really started a long time ago when I was laying the foundations for my website, nteak.com. Go check it out. I was working on a Mandelbrot renderer and eventually got to the point where I was content with it. Well, somewhat. It makes use of 4 background workers to render parts of the screen simultaneously, which is nerdy app for it paints pretty pictures. However, I eventually came to the realization that A, I was limited by the floating point resolution limit by JavaScript, and B, I was limited by the speed of JavaScript. So, I had to take drastic measures. I started learning Verilog. Hello, so today I'm going to be showing you this Mandelbrot renderer I made, and what this is doing is it's sending basically the data about the simulation, the rendering parameters, say how much of the screen we want to render and what the coordinate space coordinates are, so basically where we are in the simulation. It's sending that over to the FPGA. The FPGA is going to read that. It's going to say, okay, we've got these parameters now, and then we're going to try and calculate the Mandelbrot set for a set of pixels on the FPGA, and then we send that back over Ethernet using the lightweight IP library provided by Zynq. So yeah, we can do some exploring here in the Mandelbrot set. I've got this rendering real time, so yeah, you can see it's quite snappy. It's about 0.7 seconds per render, which is nice. I like how fast it is. And we can do some zooming here. We can do some zooming here. Yeah, it's I'm very good at my job at programming. Yeah, this noise is new. This never really used to be here. I have a feeling it's because of the 5,000 failure points on my in my design, but I'm not too sure. And yeah, it kind of does this occasionally, but I wouldn't be worried. It seems to find its way back all right. Yeah, we can do some more zooming here into some bits. Oh yeah, that's fun. Where are we? I have a feeling we're just I'm panning it so much that we're basically panning off to the edge of the screen where we can't really see anymore. There we go. I can change the zoom settings as well, the pan settings of the simulation. So I'm just doing that with my keyboard, and I've got a Python script running. And yeah, you can see that it's basically what you'd expect of a Mandelbrot rendering engine. This is Mandelbrot. Alright, cool. Well, now back to VoiceOver Nikki to talk to you about how it all works. Hello, I am VoiceOver Nikki, and today we're in Paint and I'm going to draw the block diagram of the entire rendering system. So it consists of three main different parts: the Python front end, the Zynq processing system, and the FPGA side. Now, the Zynq processing system and the FPGA side both live on the Zynq 7000 FPGA / system on chip that I'm using for this project, donated very thankfully by Focusrite Audio Engineering Limited as my internship leaving gift. So thanks to them. And what we're seeing here is the Python front end is gonna be in charge of essentially controlling the processing system. It's gonna send commands over Ethernet to the processing system, where the processing system is going to intercept those commands, and then based on what they are, it's going to do various things. So for example, we might be changing coordinates in the front end. So we want to send that to the coordinate mapper, which is programmable logic side, and that's going to transform pixel space coordinates, aka what each pixel on the screen means, to a complex arbitration of it, abstraction of it. And then that gets passed into an iteration calculator, and that's going to return how many iterations of the Mandelbrot set that pixel is. And then that gets fed back into the processing system into a frame buffer on the chip. And whenever we get a render command, that's going to basically dump the entire frame buffer over Ethernet to the front end. Now I went with Ethernet because I tried previously with SPI and UART, and you could see that the frame transfer times there are abysmal. So it's about 5 minutes per SPI and 2 minutes for UART. Whereas with Ethernet, if I really crank the packet sizes, etc., I can get about 0.2 seconds per pixel or per frame. To sort of increase speed, you can see here I just multiplied the iteration calculators, and yeah, that's all we have time for. Cheers.